Thanks. This is Carlo Apro. I'm a product manager at CNC Software, responsible for managing the integration of Mastercam for SolidWorks, multi-axis toolpad generation, and Reneshaw Productivity Plus. This presentation on building a virtual machine for simulation is part of a set of presentations dealing with Mastercam's multi-axis capabilities. When you install Mastercam, you get 17 machines. Since X5, these machines are installed with any version of Mastercam, and they represent most of the machine types out there. These machines are installed under, this is a Windows 7 system, users, public documents, shared Mastercam X6, ModuleWorks, Maxim. Every folder represents a machine, and every one of these folders contains a number of STL files, which are the models of the machine. There's a picture of the machine, this GIF file, and an XML file that governs the relationship of these models. Every machine has a kinematic tree that describes its motion. And that kinematic tree exists in this three-dimensional world, X, Y, Z, A, B, C, U, V, W. This is an industry standard, but like any standard, everybody abides by this standard a little bit differently. You can change for example, the A-axis rotary direction. Even the way you mount rotaries, it could be A could be around B, around the Y-axis on some machines. Anyhow, when you build a machine, when you look at a machine, you look at its motion. And this machine has a Y-axis connected to the base here, carrying the Z-axis and the tool. This is one side of this tree. And the other side, with the same priority here, Y-axis is attached to the base. It's carrying the A-axis rotary and a C-axis rotary. And the stock is mounted on that. This is a gantry style machine. It's actually a laser. This one has a different kinematic structure describing it. Today's task is to build this HAS VF3. This is a 3-axis machine, but we want to make it 5-axis by mounting this TR210 trunnion type rotary, both HAS products. So the first thing you need to do is actually mount it on the machine. You mount the rotary on the machine and then jog the machine around, set up the rotary device properly. And the way to do that is first we level out the A-axis. As we put it out, we make sure everything is aligned first, and then we level out the A-axis by moving along the Y-axis and rotating the A until it's flat. When it's flat, your indicator will read 0 on this end and also on this end. Once this happens, zero out your A. Say A0 is here. Next step is to indicate a machined table here. This is an OD that is ground. So we indicate this and set our X and Y axis 0. So we have A, X, Y, 0. Next thing is to rotate the A axis 90 degrees and set the indicator on this OD, on the top part of the OD, to 0. Rotate the A to plus 90 degrees, and in a perfect world it should read 0. If it's not, we're going to have to account for that, but let's say this is reading 0. Next step is to measure that OD and move half the OD, the radius, down and build a tooling tower that sets our indicator back to 0. So we move the radius, it was reading 0 up here, with the radius reading 0 here, meaning that we are in the center of this OD. Now that point on most machines won't fall perfectly on the table. On some machines it will be below the table, or some machines it will be above table. On this rotary device I measured, it was 0.1403. And this will change from machine to machine, and this is something that you should do periodically anyway. You should be double checking this number and the fact that your A is 0 periodically, especially after heavy work or, God forbid, a crash. Now, Mastercam 0, World 0, the F9 position in Mastercam, needs to coincide with the intersection of these two rotaries, this point here. The position of the part will be very important, the relative position of this part to this. Also, when you build a machine, the machine stake in the ground, when you start building a machine, is at that coordinate system there. And we call this the machine's rotary center point. Next thing is to actually jog the machine around and then sketch. I usually sketch the kinematic tree on a piece of paper. And in this case, the machine has a base, and most machines will have a base. The y-axis is connected to that. It's carrying the x-axis, the a-axis. They are abiding by the standard differently, so the b-axis is actually rotating around z. The stock is sitting on the b-axis. On the other side, we have z-axis and the tool. Let's just look at this. I have our virtual machine here. This is x, so this is what you would be doing on a real machine. Jog it around and make sure you understand how it works, and sketch up a kinematic tree, because you will need it when you're actually building the virtual replica of this machine. So that was C or B axis, and this is the A axis. Okay, so this is the way a machine moves. Next thing is you actually have to model this up. Now you may be getting models from outside, maybe from the manufacturer, and they may be in different locations. Maybe every model is scattered all over, or maybe in a different view. So you have to make sure it's sitting in a Mastercam World 0. The F9 position is coinciding with your machine's rotary center point, and you model around that. How much detail you want, that's up to you. I like to keep it organized also. I put the wireframe on level 1000, and then I put every solid model of the machine on different level in Mastercam and name them something that makes sense to me, something that I can recognize later. Oh, this is x-axis component here. I have 1, 2, 3 pieces of x-axis. The table is one piece. This rotary housing is actually part of the x-axis, because when you move the x, it's moving with it. It's not rotating when you rotate the a-axis. Only this part is rotating. Anyway, so the first thing is model the machine up. And then the next step is, and this is very important, to create a folder with the machine name, whatever you want to name the machine in. I named this machine as VF3TR. And I usually put this folder on my desktop and save this model file, the modeled up machine, into that folder, and I call it the same name. In this case, it's has VF3TR MCX6. The next step is to capture all these solid models as STL models. Just a refresher, you go to File, Save Some, select the entities you want to save. In this case, we are saving the table. This is the X1 component of my table. Call it file name. I usually keep the machine name in front, because if I'm building, say next time I'm building a Kuma X1, I want to distinguish is this which machine. So in this case, this is the Haas X1 component. Save it. You can set your tolerances here. save it. What you end up is a folder full of STL models with all the different models of that machine. You grab this folder and place it into public document shaded X6 ModuleWorks Maxim. So the whole folder goes into this location. Next thing is we need a file that we can simulate. So we need some file that has a mill toolpath on it, preferably a 5-axis toolpath if you're building a 5-axis machine. I picked this file here, and I want to be able to activate my machine simulation. If you never used it before, you can customize the settings, put the simulation startup settings icon into the toolbar. If you never used the simulation before, you will get this 5-axis head machine by default. And there is actually no machine, only kinematics with that. Just select that and simulate. Next thing we want to do is create a brand new machine. So we go to File, New Machine, and then under Settings, Windows, select Machine. What you end up is you will get a machine that will be unnamed, and now you take your piece of paper and refer to this as you building your machine. Let's start that process. It is unnamed. First I want to name that to the machine name I want to use, and it has to be exactly the same name as the folder, which is house VF2ETR in this case. Next thing we want to do is add the y-axis. We're referring to our sketch. Y is carrying X, X is carrying A-axis, A-axis is carrying the B-axis here, and then we have this dynamic element called workpiece transform or workpiece set. On the next branch, we have Z-axis attached to the base, and then it's carrying the holder. Done. We just built a 5-axis machine in a minute. Now the next thing, this is enough already to run backplot the simulation, but now we want to add meat to the skeleton. We only built the skeleton, so now we start adding the STL models that we modeled up. Call it something meaningful. This is a B-axis, so call it B1, and select the color of your choice. And then just keep going on and add geometry to every component of the machine. So every axis of the machine has models attached to them, and some of them have more than one. There is no limit of how many you have, depending on how much detail you want. Here you set your colors, something contrasting so you can visually see the machine well, and depending what is this machine for. Is it just to program? Is it for educating somebody on how to use how to create toolpaths? Is it for verifying toolpaths, or is it for marketing purposes? The detail of model will depend on that. Now here we are just adding the x-axis, and this is actually one of the ways on the x-axis. And all these models come in a correct position in the way you model it. By the way, when you model the machine, you have to have every axis sitting at 0. So x, y, even the z-axis is at 0. So the spindle of the machine z-axis will actually sit on the intersection of the dual rotary. So here we go, we have x3, and see that housing is actually part of the x-axis because it is governed by the x-axis commands in your code, not governed by the a-axis rotary. The a-axis is actually just the rotary table here. Now the next thing is to add more models. You can check the movement of the machine. And I'm just gonna skip a few beats here and keep going with adding more models. Now we have adding the z-axis here. That's the z-axis head, and then there is extension there where the spindle the spindle housing is. That's my geometry Z2. Add colors to it. Be careful about the colors. Some people go crazy with make it look like a giraffe with many colors. I find it looks more professional with 2-3 colors, but it's a personal preference. That's the spindle sitting at Z0, which is the table is actually sitting below Z0. Now we have the machine pretty much modeled. This is the basic set of machine, but you can enhance this. This machine has doors, and say we want to use this for demonstrations. I can create a linear axis, custom defined. I can say that's my left door, and you can set the direction of movement. So the door will move in the X direction. You can set limits, and then you can add more user-defined axes. Again, as many as you want. I will add a right door, and that right door will probably move in the opposite direction than the left door. So I can set the direction by just changing the +1 to -1. So now I have 2 doors, but there's no models to it, so I have to add those geometries that I created during modeling, and I call them LD1 for left door 1, and that's my left door model. And actually I got that model directly from Haas, so I didn't have to model it. I just had to assemble it in Mastercam. So left door 2 is my next piece, and that is actually the handle on the door here. And again, you can go name them something name the actual models something that is meaningful, and pick a color that you like to show the contrast there. And then door 3, more detail here. Again, level of detail is up to you. This is a little washer there. This is just showing the capability. You can model up your tool changer, palette changer, whatever else. This is a really trivial piece here, but it shows some of the capabilities. For example, we are adding a window into this door, LDW, and we want to see through that window, so we're going to call it LDW, set the color. We want a yellow tinted window, and set the transparency to whatever you prefer. So by moving this scale, we can set the transparency to whatever that we can see through that window. And we will do the same thing on the right window. Again, this is a repetitive kind of work. It's not hard. It's just it really helps to name your model something that makes sense. That's something that you remember when you actually start assembling the machine. Again, same step here, adding the translucency to the right window. And the next thing is to add, we have some enclosure on this machine. Again, this is for the marketing department, so we will say, okay, we have some models. Where was it? That's the right window, enclosure. So I call it E1. See, this is why it's important to remember the names. By default, it will be called geometry. If you don't name it something else, it will be called geometry 1, 2, 3, 4. But that may not make sense to you after assembling lots of models. So there is actually another piece to the enclosure here, like a bottom piece on this machine, and I'm probably not keeping to the standard of the machine colors, but I'm just gonna go blue. And what's missing? The windows from the enclosure are missing, so let's add that. That's EW. There we go. Set there's two windows on both sides, and I model them. It's one STL model, the two windows. You can have them separate. It's just more models. Then set try to set the translucency the same, and you can set reflectivity and everything else. Now it looks like this machine is pretty much done. At this point I could save it, or in this case I will just open my axis control and start moving things. I know that door cannot move into the other door, so what I can do is I can right click here and look at my range here. It looks like 700 millimeters will work. Yeah, that's about probably how far the door can go. So it can go from 0 to -700. So if I go to my machine, that left door component, I can set my limits. I can say that the minimum limit is -700 and the maximum is 0. By setting that, if I go back now to axis control and move my door, you can see that it's moving in those limits that I set. And this is true for every axis. So you have to go through the whole machine and set your axis for X, Y, Z, A, B, C, whatever axis you have available on this one. So this will probably be 0 to 700. Let's move it around. Oh, but I changed the direction. So I have to change the direction back to move the same way. So I will say the direction is the same way, but my limits are between 0 and 700. So now this door is moving that way. Okay, so and I can check the rest of the axes here. Let's open the doors, and this is my X. Again, I gotta set my limits. This is my, let's say, Z. Let's move the Z up. Z axis plus minus, Y plus minus. Then we have A axis plus minus, and let's just see that a little close. That's my V. Oh, V is rotating around Y, because that is by standard. I have to change that. I have to change it so it's rotating around the Z axis. Let's just go back to the machine, go to my B axis. There we go, B axis, and change that from Y direction to Z direction just by typing in 1 around Z. That's just a vector direction. And now if I go back to axis control and rotate B, it's rotating the way it should. So if I go to my A is rotating way too much, so I probably need to put some limits, and usually on a house that limit is plus minus 120. Let's see, minus 120 and plus 120. Go back to axis control. The nice thing is that you can check all this out and make sure that your rotary direction and limits are set the same as the machine. So this virtual machine is actually emulating the exact motion of your real machine. You can type in the value. I want to set my 0 to 0. This is like an MDI setting. So there is my machine. Machine is pretty much built. Oh, I didn't have all my limits set, but what I need to do is I don't want to see this enclosure and the door all the time. I want to be able to turn it off. So what I'll do is if I type in MH underscore under the model name, and I have to pick every model that I want to machine hide. That's the command that I'm doing. So every model that I prefix with this MH will be disappearing on just on one switch. Let me just do a few more here and show you. Let's do the enclosure MH underscore here, and number 2, and those windows too, I want to make them disappear. So once all this set, I have this button up here. Let's just go there. This button here, if you click on that once, things go translucent. Click twice, they disappear. Click again, they come back. This is a quick way of getting rid of that, the enclosures. And at this point, I go to save my machine, and have to name the machine, this XML file, exactly the same as the machine name was when I started, which is exactly the same as the folder name where I saved all this. And that's it. You pretty much have the machine built. At this point, you can close the machine builder before you can load the machine on. So I have a part with a file, and this one actually has a fixture on level 50. So now I have to find my machine, the one I saved, and I saved it under. I have more machines here than what comes with the install. Right there, we call it house VFTTR. We will by default, all the pieces will come in, all the parts will come in, everything that on the screen. And I want to use a fixture before I simulate from a level, and it's on level 50, and simulate. This will load the machine, and I just saved and I picked, and it comes into the simulator. The doors are closed, and if I open the doors, let's say open that door and that door. Oh, I see also that I didn't change the colors of the default part and tool. But let's just look at the simulation. The simulation looks good so far. Now I might find that this part is maybe too big for this machine, but the motion looks good. So what I want to do next is go back and change the colors of my, go to edit machine here, and this allows me to go to this workpiece transform set my fixture. So every time the fixture comes in, and this is dynamically comes in from the Mastercam file, it will be the color I choose here, the initial stock. Right now I'm not running material removal because I'm just running kind of a simulation, just motion simulation. But I'm setting all the settings for I want my part to be that color. And also the tool. The tool is one color here. I can actually set the holder, the arbor, and the shaft and the flute to different colors. And I like to do that because it's much more meaningful. And this is the area that I'm closely monitoring when I'm running parts through the simulator. So once you made these changes, you have to resave the machine because this wasn't saved the last time. So you have to go save as. Make sure you save it under that name in that folder. And if you want to run the simulator again, you will have to unload this and load it up again and go from there. This is just going, starting this whole thing again. So this is pretty much it. Let me just start this, stop this, and just go over here. Once you have all this done, you save the machine, and when you save that part file, the way it was right now, you pick the machine that you wanted to simulate on, if you pick that part file, save that part file, it will remember what machine you use for simulation the next time. And it will be a great way of remembering where was the job running the last time. So this is pretty much it for building a virtual machine for simulation. There is more to this. I mean, you can add collision checking, and there is other capabilities that we didn't really cover here, but this is enough to get you going and start building machines. If there is any questions, please don't hesitate to ask. I will be standing by. Thank you.